Good morning, and thanks very much, Luke, for this question. And let's go through it now. I thought it was a pretty tough one, and I think I probably spent about 40 minutes doing it last night. You can see that we've been given a sketch to do, and there's a few things that we should consider. Firstly, we want to see that t is greater than 0, and we seem to have, if we look at it, a function in t with respect to dt. So if I'm going to start with drawing the axes, I'm going to have a y-axis and a t-axis, and that would mean I'd possibly be able to sketch this second part as well. So here's my artistic effort. We can see there's my t-axis and my y-axis. So we've got some function of t. Now we've been told that f of 0 is equal to 0, and f of x is going to be obviously equal to f of x. And so, we've been told that the gradient is always positive. So I've just made up a curve there, and I think that the integral between 0 and x of f of t must look something like that area shaded in. The second one looked much more worrying. We were told that the inverse of f with a y input, well, that's just a weird way of writing the function of t, isn't it? It's the same thing, but this time we are asked to integrate with respect to y. So we've got the same graph, and we've got the same x and f of x values on the t and y axes respectively. So because I'm integrating with respect to y, that's the area I would be finding, isn't it? And I hope you can see that if you combine those two areas, you end up with a rectangle whose the base is x and the height is f of x. So we've answered the first part of the question. Okay, so looking at the part 1, we're told that we've got a real function, g is defined. That's going to be important later on, and it's defined for all t. And they've given us some way of evaluating or linking the function with its input, and they've given us, we've got to prove this time that g of 0 is equal to 0, and that the gradient function is positive for all t. Okay, so let's do that first. Here we go. Okay, so now we're looking at proving what they asked us to do, the first bit, that g of 0 equals 0. And so if we stick that into the equation they've given us, you'll see that g of 0 all cubed plus g of 0 has to equal 0. Now we can factorise that expression, and I think it's important that you do, because while it's obvious that g of 0 equals 0 is a solution to that first part, it's not the only solution possibly. So if you factorise it, you get g of 0 multiplied by g of 0 all squared plus 1 equals 0. And it turns out, of course, that g of 0 is equal to 0 in this case as a real solution. The other factor, though, the g of 0 squared can't equal minus 1 if we're only having real solutions, which is what this question said, that we are to consider real solutions only. So in actual fact, yes, g of 0 is equal to 0 and only equal to 0 in the real numbers. As for getting the gradient function, well, differentiating is easy enough, and I've written it down there. And if you factor out the g prime of t, you can write that as a fraction, 1 over 3 gt all squared plus 1. Now, you can see that the g of t is squared here, so it doesn't matter whether you're getting positive or negative values, that's always going to be positive, and so we've got 1 divided by a positive number, so therefore the gradient function must always be greater than 0, which is what they asked us to show. Okay, so now we're looking at evaluating the integral of g of t with respect to t between the t values of 0 and 2. Well, let's use that initial formula that we proved at the very start of the question. This time I've converted it to make sense for rather than x f of x, but x g of x, but it's the same idea. And I've written it down carefully. I've been a little bit naughty with the second term, that integral between 0 and g of x with the inverse function. I should really have written g of 0. Now I know that we've shown that g of 0 is 0, but I should be entering y values on that integral, and not I mustn't confuse myself and think that's a t value. Okay, so I hope you can see where I've got that first equation from, and that points out a few things that we need to work out. We need to work out what is the value of g of 2, and what is the value of g of 0, and we know that the gradient function is always positive. Okay, so let's get on with that then. So we've been given the formula to convert our g's of t's into a t value. So using that, we can factorize a solution initially, because we can see that 1 cubed plus 1 equals 2. So therefore 1 must be a solution, but it's not the only solution. We should check the other, and it turns out that g of 2 must equal 1. And the second factor, the g2 squared plus g2 plus 2, again, has no real solutions, so I don't need to consider that any further, but I must show that I have thought of it. Right, and then so I've got my value of g of 2 and my value of g of 0, so I think I'm good to go. So here we go. Let's look at the bottom of this page. You can see that I've got xg of x, which is going to be 2g of 2. I think I've set everything else in carefully. Again, I shouldn't have put 0, I should have put g of 0, but never mind. And yeah, g of 2 is equal to 1. Change the integral, integrated y cubed plus y to get a quarter y to the power of 4 plus a half y squared. Substitute my values, and then I've got 5 quarters. Okay, so for the last part, we've got a very similar question. This time it's going to be t plus 2. Just looking at it, we're going to use the same initial definition right at the top of the question. It looks clear that we're going to have to evaluate h of 8 and h of 0. We should also check out the gradient function, make sure it's positive. Okay, let's get on with it. So again, let's set the problem up rather than trying to evaluate h of t between 8 and 0 with respect to t. Let's set it up as the initial part of this question has, and I've written that up for you. I can see immediately that I've done something a little bit silly. I've done the second term, an integral between h of x and 0. Of course, that should be h of 0. So sorry about that. But otherwise, I think it's clear that we've got to work out what is the value of h of 8, h of 0, and we need to work out what the inverse function of h would look like. So let's get on with it. So again, there's my second line down here. I've made that silly mistake. But anyway, let's get the value of h of 8. So if I stick h of 8 into my formula, I'm going to get h of 8 cubed plus h of 8 is equal to 10. Now, clearly, something cubed plus something is going to equal 10. That would suggest that h of 8 is equal to 2 as an immediate solution. But just like we have in the previous parts, we're going to have to go and factorize that to make sure there's no other solutions. And again, it turns out that there is, for this, complementary sort of function here, we've got an m squared plus 2m plus 5 is going to have no real solution. So we can forget the second factor. We should also check out what is the value of h of 0. So h of 0 cubed plus h of 0 equals 2 would suggest that h of 0 is equal to 1, and again if you factorise it you'll find that there are no other real solutions. So now we've got the value of h of 8 is 2 and the value of h of 0 is 1. We know the limits of our integral. We need to work out the inverse of h now, don't we? So if we say that y is equal to h of t, then if I find the inverse, t is obviously to the inverse of y, and we know that y cubed plus y minus 2 is equal to that inverse. So returning to our solution, here we go. We just need to stick in the figures now, and I've corrected my initial error. That's good. Okay, so I've got 8, h of 8. Yeah, that all seems to follow the initial equation, and substituting out the h minus 1 of y with its equivalent. Yeah, good. And integrating, I haven't integrated that. Oh, I have this time. That's good. Okay, and yeah, it's all looking good. And so I think the answer is 12 3/4. I'm just trying to think, have I done everything I should have? No, I haven't. I didn't check to see that the gradient function of h is always positive. So I possibly have lost a couple of marks there, but that's something that definitely we can do.